it's just a little Venn diagram looking at it, and we're starting off with the word energy because that's what our topic is, and a lot of from here on out is going to be energy, different forms or types of energies. Now, I said this before, and I'm going to say it again, that it doesn't matter what type of energy. Is it the energy that we were talking about yesterday that is potential or kinetic or mechanical, renewable, non-renewable, thermal, radiant or light energy, sound energy, electrical, all the energies all have the same SI unit, which is a joule. Now, when energy is broken up, and kind of like yesterday in our notes, I'm just going to go backwards over here where they said, yeah, we have 7 different types of energy, and all energy can be grouped, not only grouped into kinetic or potential, but we also saw in our notes yesterday that our energies, we also have groups called, renewable, non-renewable energies, right? But these main 7 types of energies that we see in our everyday lives, and we probably use it because you probably got into a vehicle and you use some gasoline to come to school. You probably you may have ate breakfast, or maybe you're not a breakfast person. You're going to eat lunch. Okay, that's another type of energy, right? Chemical energy. So we use these 7 everyday energies all the time, broken into 2 categories, kinetic and potential. So over here, they're breaking those 7 groups of types of energies into what we called potential, or kinetic, right? And we definitely know, or we use those middle school easier terms, right? This is when that is physically being used or moving. And then this is stored. It's not used right now, but it's got the potential to be used or to cause movement or to cause work. Oh, there you go, work to be done. Now, kinetic, which I think really like the basic term that we first are introduced is energy and motion. All right, you probably watched a couple of these cheesy videos a long time ago. It has an equation, and I know that this is a middle school equation because I have a middle schooler, and they have to do this equation as well. It's the same equation, 1/2 mv squared. So the equation that you did in middle school, we're coming back to do it again. Next one over here is potential energy. Now, there's 2 types of potential energies. The one that you are probably more commonly familiar with is GPE, or sometimes it's written in the way of PEG. Gravitational potential energy. That one is probably a common familiar one. I know that these 2 equations, because this equation is MGH, these 2 equations are a middle school equations that you need to do then. But this one is a new one over here. This is a high school one. From high school on, this is a new one that we toss in. We wait till you get a little bit older before we toss another one in. Okay? This GPE that's familiar to you is going to be due to height. Right? How high up is it? And the higher it is, the more potential energy it's going to have. Also, we know from kinematic equations, the higher up it is, the more time it's going to allow for gravity to cause an increase in that acceleration, and it's going to pick up speed. See, so we learned that, which now makes sense to this that you learned in middle school, MGH. The higher it is, the more potential energy it has. This one over here, which is our new one, is going to be due to stretchy. Due to stretchiness, due to stretchy. What do you mean, Miss Munson? Wait a minute, did I misspell it? Did I miss an A? Is there an A on there? Yeah, huh? I think there is stretch. I think I misspelled it. Oh, that's all right. Due to stretchy. Now, due to stretchy for us is called PEE. PEE. PEE stands for elastic potential energy. Now that makes sense. Due to stretchy. Now, this equation over here, let me stop for a moment and I want to double check because I have it for some reason on one spot, I have it highlighted, and on another spot, I do not have it highlighted. And I'm almost sure that it is, yes. Let me double check. Elastic, oh, it was there this whole time, potential energy, 1/2 times the spring constant, which is a K variable, times the distance of the stretch. Oh, I did not misspell it. Oh, I did, missing a T, right? Stretch, E, let me go ahead and fix that. T, stretchy, there we go. Squared. Oh, good, it's on the formula chart. I don't need to highlight it. Yes, I feel happy now. Alrighty, so this equation is 1/2 K D squared. Alrighty, 1/2 K D squared. And it's on the formula chart. We saw that just a second ago, so that is really good. So this is right now a new equation. These two equations you had in middle school, so you should be good to go with those. Now, continuing with our notes, so that way we can, we have a little bit more time, and then I need to get to our test. It says here, what is potential energy? Now, potential energy is going to be, stored energy as the result of its position. Now, the units are in joules, don't forget that. But a result due to its position. What is potential energy? Now, don't forget, though, there are two different forms of potential. There's gravitational, meaning the higher it is due to its height, its position, or now there's this new one that we really haven't looked at too much yet, but we just talked about. It's called elastic, which also is due to its position, meaning the further, and we've all probably done this, right? You've probably pulled back a rubber band and let it go. But if you pulled a rubber band back a little bit more because you want it to go further, you want it to have more elastic potential energy, you want it to hurt that other person when you hit them with it a little bit harder of a sting, right? So it's also due to its position. It says here examples. So they're going to go a little bit into gravitational first, and then they'll start talking about elastic. It says here, a heavy ball on a demolition machine. So the more that we rise and pick this up a little bit higher, when they release it, or if they are to pull it back a little bit more and release it, it would have more potential energy, right? It says here, it would have more the higher elevated position. But, remember that word position, if, for an example, you were to pull back, they didn't use a rubber band, but they're using, if you were to drawn back this bow and arrow, and the more you pull it back, the more of that elastic potential energy to allow that arrow to go further out. Okay, same thing though with the rubber band. It says over here, when we look at this picture for an example, looks like we're talking about a little bit of GPE. Where would the ball have the highest potential energy? This is like guarantee you're going to pass this, right? Because this one's going to be pretty easy. At the top. Why? Well, because of its location. Or, how about that word position, right? And then it says over here, well, where would the ball have the lowest potential energy? Actually, at the bottom, literally at the bottom. And we can see that at the bottom, the actual potential energy here is going to be 0 joules. That's a legit, number, 0 joules. Negative would not ever be valid. There you go. We've used negative in the past regarding direction, but negative wouldn't be valid. That would be indicating you're missing, you lost it, which wouldn't be okay. Okay, but 0 absolutely is a good number. Turn the page. So just looking at the GPE equation, which again, we already wrote it down. It's not a hard one. You probably are very familiar with this GPE equation, which is mgh. Those 3 variables are being multiplied by each other. GPE having an SI unit of a joule. Any type of energy is going to have an SI unit of a joule. M is going to be mass, and mass we know needs to be in kilograms. G is going to be gravity. And gravity has a constant number, right? It's 9.81 meters per second square. And then after that, H or HT, just depending on how it's written out, we know that's going to be its height. So I'm just going to write HT. And height is a distance, which needs to be in meters. If it's not, you need to convert it. Now, the first one over here, number 1, says that there is a cart that is loaded with a brick and pulled at a constant speed along an inclined plane. Okay? If the mass of this load is 3 kilograms, M, and it's in kilograms, which is good, and the height at the top is, I'm going to put H for height, 0.45 meters, so that's in meters. That looks good. Well, then what is the potential energy? Question mark, not only PE, but this is GPE because we're talking about the height, the location, the distance. Okay, so GPE equals MGH, and they don't need to give me G because I already know that number. M is 3, G is 9.81, and then H is 0.45 meters. My major concern would probably be just to make sure that nothing is in the wrong unit, and that would equal blank joules. But the next question says, if a force, capital F for force, is 14.7 newtons, is used to drag a load along an inclined plane at the distance, of 0.9 meters, then how much work, question mark W, was done? Well, if I recall, because that was last unit, and everything kind of starts to build on each other. Work equals force times distance, if you recall that. We're looking for the work, and thank goodness they gave me the force. But if they did not give me the force, remember, and they gave me the mass, I would then get that mass and multiply it by 9.81 to get the force. But for this situation, it was given to me 14.7 multiplied by the distance of 0.9 meters. I would get blank joules. Now, there was a reason for me to put that word problem in there. I hope you see one commonality between them, is that one of them was talking about work and the other one was talking about GPE, but they both have the same SI unit of a joule, okay? We're about to get to that point. We're about to smash equations together, kind of like how we did with kinematics, and we're going to have a new one, and it's going to be a Superhero Power Ranger morph energy equation that we're going to smash together pretty soon. Because I can see that if you have energy, you can do work. And I also see that the SI units for energy and work are the same thing. So there must be something that coincides, a commonality between the two, and there is. Okay? Now, the next problem over here talks about the rock, and I'm not going to do that at this moment. That might just be left for you to work on as a GPE problem. Let's go into elastic potential energy, and then I will shut this down pretty soon in a little bit. Let's go ahead and fill in a little bit of this. So again, still talking about potential energy, but elastic potential energy. We touched that just a second ago a little bit. PEE is the energy stored in elastic materials. As a result of their stretchy or stretching or stretchy, whichever word you want to use. Examples, a rubber band, a bungee cord, trampolines, a spring, a hair scrunchie, a bow and arrow when you pull back on that bow. Okay? There are quite a few examples that even we use quite often. Okay? It says here that the amount of elastic potential energy stored in such a device is related to the amount of, it says here, stretch of the device. The more stretch, the more stored energy it has in there. It says here, but springs are a little special. Springs are a little special, and not all springs, but some springs. They're a little special in the case that for this device, they can store elastic potential energy not only due to their stretch, or they're special because not only can you stretch a spring, for an example, let's see, I'm sure this pen has it because it's a clicky pen. Here it is. Not only it's stretch, but also when I leave it there, I can also do what? Compress it. I can also compress it and smush it down. So springs are a little different or a little special because it's not only due to their stretch or compression. This equation that we're talking about right now is going to hit us again second semester. Okay, so now springs are a little special because it's not only due to their stretch but also their compression. Not all springs, but a good chunk of springs that are out there. It says here that a force is required to compress that spring or even stretch it, to be honest. Okay, and the more compression or stretch there is, it says here, then in that case, the more force that is required to compress it even further. It says here, we actually call this Hooke's law. If a spring is not stretched or compressed, like earlier when I had that spring out and it was just sitting there, when it's not stretched or compressed, it says here that in that situation, there is no elastic energy stored in it. It has a number of 0 joules. And remember, like I said earlier, 0 joules is a completely acceptable answer. but a negative is not acceptable. The spring, it says here, is said to be in what we call equilibrium position. Equilibrium position. And the equilibrium position could be called, it says here, the rest, or I'm going to put right here, at. I'm going to put a little line, at rest, which equals 0 joules. Remember, negative is not acceptable. Negative is not okay. 0, that's acceptable. When you turn the page, we're going to write down that equation, and then we're going to do a few practice problems, and then I need to pass back that test to you to go over that in just a moment. So one more time, equilibrium, for an example, is whenever it's just sitting there at rest, and the answer or value of its energy is 0 joules. Negative is not acceptable. Springs are a little special because you can stretch them or compress them. So on the next page over here, this equation we looked earlier, it is on the formula chart, which is great. It is, and we wrote it down. Where am I at? PEE equals 1/2 K, it's truly a lowercase k, times distance squared. A distance as in how much did you stretch it or compress it from the rest position? How much did it get compressed or stretched from the rest position? And so the PEE stands for elastic potential energy. And we definitely already know that its SI unit is a joule. The K is actually what we call spring constant. And it has an SI unit of is newtons per meter. Newtons per meter. Not a Newton meter, which is torque, but newtons per meter. Okay, now I want to pause for a moment because it says the word constant. Ms. Munson, does that mean that it's going to be like one of these constants over here on the formula chart? No, it's not. What they mean here for this situation, a spring constant, is that every spring has its own constant, or every rubber band. You can go and, I don't know, to like an office supply store, and you can go look at the rubber bands, and there's different thickness, right? Because some of them are super thin and they stretch and they're not so strong or firm. Some of them are a little bit thicker and they have more firmness to them. Every rubber band in the same bag is going to have the same spring constant number, okay, if that makes sense. Unless you buy like that mixture of rubber bands, well, then they're all going to be a little different. And then X or D, we've used that earlier this school year, stands for distance, position, location. And we know that it should be in meters. Okay, so I'm going to come over here and I'm going to practice the second one right here. When it says 13.2 joules, and then we can stop. Whoa, this is energy. I'm just going to put it. Energy is given, because what kind of energy? Is it potential? Is it elastic? Is it gravitational? I'm just going to put an E right now. Energy is given to a vertical spring. Oh, wait a minute. PEE, because they use the word spring. The spring's compressed to a distance, location, position, all of those words work. And so I'm going to put it right here, lowercase d, a 0.0593 meters. Find the constant, question mark, K. Find the spring constant, or the K value. So my equation for elastic potential energy is PEE equals 1/2 times K times D squared. Alrighty, well, 1/2 is, 0.5, so they don't need to give us that number. We're actually looking for the K. I have the distance, I have the PEE, and I do have the 0.5. So looks like I can solve for this. Let's plug it in. I've got 13.2 equals 0.5. I change the 1/2 to the 0.5, multiply it by K, which I do not know and I'm looking for. Multiply it by the distance, which is 0.0593. Please don't forget to square it. All right, let's go ahead, and we're just doing basic algebra. That's it, nothing hard. Well, I need to go ahead and isolate and get K by itself, so let's go ahead and divide this side by 0.5, and I'm going to multiply this side by 0.0593 squared. Now I get to cancel those out. So I'm going to do it to the other side as well, because what you do on one side, you've got to do on the other. 0.5 times 0.0593 squared, and that's going to give me my K value. Pretty easy cheesy, I think. That is going to give you your blank newtons per meter, right? Not a Newton meter, because that's torque, but newtons per meter is the correct SI unit. Alrighty, so we are done with that.